In the next pair of videos, I'm going to show you how to do definite integrals using u-substitutions. Let's start off with problem number 62 from page 306. The integral from 0 to 1 of x cubed times 2x to the fourth plus 1 squared. Since the 2x to the fourth plus 1 is inside the squaring function, that makes it a good candidate for my u-substitution. So let's set u equal 2x to the fourth plus 1. Calculating the differential, I get 8x cubed dx. Well, that's promising. I have an x cubed dx and can easily multiply and divide by 8. So let's rearrange things a little bit. I'll move the x cubed over with the dx. And in order to get the 8 in front of the x cubed, I'll multiply and divide by 8. So, making our substitutions, the 8x cubed dx becomes du. The 2x to the fourth plus 1 squared becomes u squared. But hold on. We need to figure out what the new bounds are. Even though I haven't been writing it down, in this integral, we're integrating from 0 to 1 on the x-axis. So in other words, we're going from x equals 0 to x equals 1. Down here, I need the bounds for u. Those might be different from the bounds for x. Let's find out. If we look over at this formula, we see that u is 2x to the fourth plus 1. So as in this upper bound, we have x equal to 1. If we take that 1 and we substitute it for x, we get that u is 2 times 1 to the fourth plus 1, which is 2 plus 1, or 3. So x equals 1 corresponds to u equaling to 3. So my upper bound is u equals 3. For the lower bound, for the x's, x equals 0. And if I substitute x equal to 0 into my substitution, I get that u is 2 times 0 to the fourth plus 1, which is 1. So when x equals 0, u equals 1. So my lower bound for u is 1. Now we're ready to proceed. The antiderivative of u squared is 1/3 u cubed. And I'm going to take that from u equals 1 to u equals 3. An eighth times a third is 1/24. And let's substitute in for u. I'll have 1/24 times 3 cubed minus 1/24 times 1 cubed, which is 27/24 minus 1/24, which is 26 over 24, which simplifies to 13 over 12. And that's the value of the integral. Now, something that you can notice is that when we do definite integrals using this method, there's no point down here that I end up substituting the x's back in, like when we do antiderivatives. Let's look at another example. This one is number 66. And that's the integral from 0 to 2 of x over the square root of 1 plus 2x squared. So I see 1 plus 2x squared inside a square root, so I'm going to use that as my u. In calculating the differential, the derivative of 1 plus 2x squared is 4x, and then I multiply by dx to make it a differential. So I have an x dx. Let me rewrite this so that my substitution will be a little bit more obvious. I can write the 1 over square root of 1 plus 2x squared as 1 plus 2x squared to the negative 1/2 power, and I'll write the x over with the dx. Now, since I need a 4x dx, I will multiply by 4 and divide by 4. And then the 4x dx becomes du. The 1 plus 2x squared to the negative 1/2 becomes u to the negative 1/2. And last of all, let's change the x bounds into u bounds. So the bounds on x are 0 at the bottom and 2 at the top. Let's start off with x equals 2. If x is 2, then u is 1 plus 2 times 2 squared, which is 9. And if x is equal to 0, then u is 1 plus 2 times 0 squared, which is 1. So x equals 2 corresponds to u equals 9. X equals 0 corresponds to u equals 1. Now let's carry out the integral. The antiderivative of u to the negative 1/2 is obtained by adding 1 to the exponent, which gives me u to the positive 1/2, and then multiplying by the reciprocal of the new exponent. Simplifying a bit, 1/4 times 2 is 1/2. So I have 1/2 of 9 to the 1/2 minus 1/2 of 1 to the 1/2. The square root of 9 is 3, so I have 3/2 minus the square root of 1 is 1/2, and 3/2 minus 1/2 is 1.